In October of 1927, 29 people checked into a hotel in Brussels to settle an argument. Between them, they would eventually hold 17 Nobel Prizes. The argument was about a new theory that had just started working better than anything anyone had ever built. And the question on the table was simple. What is it actually telling us about the world? They spent a week on it. The arguments ran through breakfast. Then everyone went home, and it was not settled. 100 years later, a survey went out to more than 1,000 physicists asking that same question, and the answers came back scattered across 6 incompatible pictures of reality. Something in that theory is still frightening the people who use it every day. So what is in there? And out of every strange thing quantum physics has ever produced, why is there one they cannot get past? Get comfortable. Subscribe if you have not already, and stay with us, because we are going to walk through 7 of those strange things one at a time. And the reason this takes an evening is that the answer only makes sense once you have seen all 7. Let's begin. Part 1. The machine that works and cannot be read. There is a machine in your pocket right now that has never once been wrong about anything you asked it to do, and nobody who built it can tell you what it means. I want to be precise about that, because it sounds like a figure of speech and it is not one. The chip inside your phone works because of quantum mechanics. So does the laser in the scanner at the supermarket, and the light-emitting diode in the standby light on your television, and the magnetic resonance scanner in the basement of your local hospital, and the atomic clocks aboard the satellites that let your car know which street it is on. Quantum mechanics is not an exotic corner of physics that occasionally gets mentioned in documentaries. It is the operating system of the material world, and every piece of technology invented in the last 80 years runs on top of it. And it is accurate. Not approximately accurate. Accurate in a way that has no real parallel anywhere else in science. There is a number in quantum electrodynamics called the magnetic moment of the electron. You can calculate it from theory. You can also measure it by trapping a single electron in a magnetic bottle and watching how it wobbles. Those two numbers agree to about 12 significant figures. That is like predicting the distance from London to New York and being off by less than the width of a human hair. Nobody in any other field of human knowledge has ever produced agreement like that between an idea and a measurement. So here is the thing that should stop you. The people who built this theory could not agree on what it says about the world. And 100 years later, the people who use it every day still cannot. The reason is not mysterious once you see it, and I want to lay it out plainly, because everything else in this video sits on top of it. Quantum mechanics has 2 moving parts, and they do not fit together. The first part is the equation. It is called the Schrödinger equation, and it describes how a quantum system changes over time when nothing is disturbing it. It is beautifully behaved. It is linear, which means you can add solutions together and get another solution. It is deterministic, which means if you tell it the state of the system now, it hands you the state later with no ambiguity at all. And it is reversible, which means you can run it backwards just as easily as forwards. There is nothing probabilistic in it. Nothing in that equation gambles, hedges, or picks. It is arguably the best behaved object in all of physics. The second part is what happens when you look. And when you look, you do not see the smooth spread of possibilities the first part describes. You see one thing, one position, one outcome, one result on one dial. So the theory has a second rule bolted onto the side of it to handle this. It says, when a measurement occurs, the probability of each possible outcome is given by a specific formula, and after the measurement, the description of the system snaps to whatever you actually got. This second rule is not linear. It is not deterministic. It is not reversible. It is, in every important respect, the opposite of the first rule, and here is the gap. The theory never says when to switch from one rule to the other. Read that again, because people assume they have misunderstood it. There is no equation anywhere in quantum mechanics that specifies what counts as a measurement. Not how many particles are required, not whether a detector is enough, or a photographic plate, or a screen, or a click in a set of headphones, or a mark on a piece of paper, or a person's eye, or a person's memory of what their eye saw. The theory contains the word measurement in its foundational rules, and it does not define it. In mathematics, you would call that an undefined primitive term, like the word point in geometry. It is something the system uses and never explains. John von Neumann worked this out formally in 1932, and what he found was worse than an omission. He showed that you can put the dividing line anywhere you want. Draw it between the atom and the detector. The predictions come out the same. Draw it between the detector and the room. The predictions come out the same. Draw it between the room and the scientist's retina, or between the retina and the thought in the scientist's head. Still the same. The line slides freely across the entire chain, and nothing you can measure ever changes. Later, physicists gave the thing a name. They called it the shifty split. That movability is not a convenience. It is the whole problem. If the location of the boundary made a measurable difference, we could go and measure it and settle the argument in an afternoon. It does not. So there is a question at the exact center of the most successful theory in human history that no experiment can answer, and it is not because we have not built the right equipment. It is because the theory is constructed in a way that makes the question invisible to equipment. I find it useful to think of it like this, and I'm going to come back to this image at the end of tonight, so hold on to it. Imagine you own a phone that works perfectly. Calls connect, messages send, the battery lasts. It has never let you down once. But every so often, not often, maybe once a month, the screen flashes for a fraction of a second with a set of symbols you have never seen before, in a character set that is not in any language you can find, and then goes back to normal. The phone still works. Nothing has broken. You could go your whole life ignoring the flashes and the phone would never fail you. I say 1927 for a reason. That October, 29 of the most capable physicists alive gathered in Brussels for the 5th Solvay conference, and 17 of the people in that room would eventually hold Nobel Prizes. The subject was the new quantum theory. What is remembered from that week is the running argument between Albert Einstein and Niels Bohr, conducted partly over breakfast, in which Einstein would arrive each morning with a fresh thought experiment designed to show that the theory could not be the final word, and Bohr would spend the day taking it apart. Bohr won most of the exchanges on the technical points. He did not win the argument. Einstein went to his grave convinced that quantum mechanics, whatever else it was incomplete. And the disagreement that started in that room has never been resolved. It was not settled. It was set aside, and the field got on with the work, but you would want to know what they said. And more than that, you would start to wonder what kind of machine you were actually holding. That is the situation physics has been in since about 1927. The phone works, the flashes are real and repeatable and documented in peer-reviewed journals, and everybody in the field knows about them, and nobody can read them. Tonight I want to show you 7 of those flashes. 7 famous paradoxes in quantum physics, all of them real, all of them built on experiments that have actually been performed, most of them confirmed multiple times in multiple laboratories on multiple continents. One of them appears to show the future reaching back and changing the past. One of them appears to show 2 people in the same building disagreeing about whether an event happened at all. One appears to show 2 strangers coordinating a perfect answer without exchanging a single bit of information. One appears to show an object separating from its own properties, so that the thing goes one way and what it is like goes the other. One suggests, if you follow it honestly, that you personally may never experience your own death. One takes place at the edge of a black hole and pits general relativity against quantum mechanics, with no obvious way for both to survive. And the last one is not exotic at all. It is so plain that most people hearing it assume it must be a technicality. Here is what I am not going to do. I am not going to tell you which of the 7 is the one that actually frightens the people who work on this. Not yet. That is the question this whole video is built around, and by the time we get to the end of it you will know the answer, and I think it will not be the one you expect right now. Because the strange thing about this list, the thing that took the field the better part of a century to notice, and that only became formal in a paper published in 2025, is not how different these 7 problems are from each other. It is how they are not different at all. Part 2. The people who built it and could not live with it. In 1965, Richard Feynman stood in front of a lecture hall at Cornell University and said something that a person in his position is not really supposed to say. The lectures were called the Messenger Lectures, and they were later published as a book called The Character of Physical Law. Feynman was, at that point, one of the 2 or 3 most formidable physicists on the planet. He had built a large part of quantum electrodynamics himself. He had invented a way of drawing quantum interactions that every physicist since has used. He would win the Nobel Prize the same year. And what he told that lecture hall was this: I think I can safely say that nobody understands quantum mechanics. Not, it is difficult. Not, it takes years to learn. Nobody understands it, including, by clear implication, him. You will hear that line quoted a lot, and it is usually delivered as a kind of charming modesty, the great man being humble in public. I do not think that is what it was. I think he meant it as a technical statement about the state of the field, and I think the reason it has survived for 60 years is that everyone who works in the field recognizes it as accurate. He was not the only one, and he was not even the most uncomfortable. Niels Bohr, who spent his life defending the theory against Einstein, said that anyone who is not shocked by quantum theory, when they first come across it, cannot possibly have understood it. That is a strange thing for a defender to say. It is an admission that the correct reaction to the theory is not comprehension, but a kind of recoil, and that anyone who feels comfortable has almost certainly missed something. Roger Penrose, who has spent decades working on the relationship between quantum mechanics and gravity, has been blunter than either of them. His position, stated in public more than once, is that quantum mechanics makes absolutely no sense. Not that it is hard, not that it is counterintuitive, but that as a description of what is actually there it does not cohere, and that this is a signal that something in it is incomplete. And then there is Erwin Schrödinger, who wrote the equation. The central equation of the theory, the one I described in the last part, the well-behaved one. His name is on it. And there is a remark that circulates, reported by Werner Heisenberg from an argument the two of them had in Copenhagen in 1926, which comes down to us in various forms, the shortest being that he did not like it, and he was sorry he had ever had anything to do with it. I want to flag that the short version you see on posters is a paraphrase rather than a documented sentence. What Heisenberg actually reports is Schrödinger saying that if all this business of quantum jumping were really here to stay, he should be sorry he ever got involved with quantum theory. The sentiment is the same either way, and the sentiment is remarkable. The man wrote the equation. He then spent a substantial part of his career trying to find a way to interpret his own work that he could live with, and he never found one. Einstein is the famous holdout, and it is worth being careful about what he actually said, because he is quoted loosely more than almost anyone in science. There is a line floating around in which he supposedly said that if quantum theory were correct, it would signify the end of physics as a science. I have not been able to trace that one to a solid source, so I am going to leave it where I found it. What he definitely did was co-write a paper in 1935 with Boris Podolsky and Nathan Rosen arguing that quantum mechanics could not be a complete description of reality. And what he definitely did write, in a letter to Max Born in 1947, was that he could not seriously believe in the theory because it could not be reconciled with the idea that physics should represent a reality in time and space, free from what he called spooky action at a distance. There is a fifth name that belongs in this list and almost never appears in it. In 1932, John von Neumann published the book that put quantum mechanics on rigorous mathematical footing, and in it he included a proof that hidden variable theories, the idea Einstein wanted in which particles have real properties we simply cannot see, were impossible. That proof shut the door on an entire line of inquiry for a generation. In 1935, a young German mathematician named Greta Hermann published a paper pointing out that the proof rested on an assumption that had no justification and that the door was not shut at all. Nobody listened. Her objection sat unread for 3 decades until John Bell independently found the same flaw in 1966 and said so loudly enough to be heard. 30 years of a field being wrong about what was possible, because the person who noticed was not the sort of person the field was listening to. Every one of these people is describing the same discomfort, and none of them is describing a mathematical error. They all agreed the mathematics worked. That was never the argument. The argument was about what the mathematics was a description of. Now, you might reasonably assume this is history. Old men arguing in the 1920s, long since sorted out by better equipment and cleverer people. That assumption is wrong, and we have unusually good evidence that it is wrong, because in July 2025 the journal Nature ran a survey to mark the 100th anniversary of quantum mechanics and asked physicists directly what they thought their own theory meant. 1,101 of them answered. The results are worth sitting with. The largest single group at 36% back the Copenhagen interpretation, which is roughly the position Bohr staked out, and which is also, not coincidentally, the version taught in almost every undergraduate physics course in the world. Second place, at 17%, went to information-based approaches, which hold that the quantum state describes what an observer knows rather than what is there. 15% backed the many worlds interpretation. 7% backed the pilot wave picture, in which particles have definite positions at all times and are steered by an invisible guiding field. And 16% declined all of the options they were offered, and wrote in their own answers, some of which amounted to saying that the question itself was badly formed. But the number that stops me is a different one. Of everybody who picked a favourite interpretation, only 24% said they thought it was actually correct. Not adequate. Not useful. Correct. Everyone else described their own preferred view of reality as a serviceable tool, or as good enough for the circumstances they work in. Think about what that means. 3/4 of the professional physicists surveyed, asked what their own most successful theory says about the world, gave an answer they do not fully believe. There was exactly one thing they nearly agreed on. 86% said that trying to interpret the mathematics physically, trying to work out what it means, rather than just using it, is worth doing. Which is to say, the closest thing to consensus in the field is that the question is important, not the answer, the question. So this is not a story about people who found something out and are keeping quiet. There is no suppressed result. Nature published the disagreement on purpose, in its centenary year, on the front of the magazine. The papers I am going to describe tonight are in Nature Physics, in Nature Communications, in Physical Review Letters, in Science Advances. Nothing here is hidden. What there is instead is a working habit, and it has a name. In 1989, the physicist David Mermin, writing in Physics Today, coined a phrase to describe the standard professional response to all of this. Shut up and calculate. It is habitually misattributed to Feynman, which is its own small irony. It means the equations give the right answers, so use them, get results, publish, and do not spend your career on a question with no experimental handle. It is not cowardice, it is triage. But it was strong enough for long enough that John Bell, the man who eventually found the single most important experimental handle anyone has ever found on this problem, did a good deal of his foundational work while on unpaid leave from his actual job. Bell himself eventually lost patience with the vocabulary altogether. In 1990, in an essay bluntly titled Against Measurement, he listed the words he thought should be banned outright from any serious statement of what quantum mechanics says: system, apparatus, environment, microscopic, macroscopic, reversible, irreversible, observable, information, and measurement. His argument was that every one of those words smuggles in a division of the world that the theory itself does not supply, and that using them lets you feel like you have explained something when you have only relabeled the gap. So the crack has been there since the beginning, and what the field learned to do, very early, was paint over it and keep moving. The question is, what happens when you stop painting? Part 3. The experiment that looks like it reaches backwards. The first flash on the screen is the one that looks like time travel. To get to it, I have to walk you through the most famous experiment in physics, briefly, because everything else is built on it. Fire particles one at a time at a barrier with 2 narrow slits in it, and put a screen behind the barrier to record where they land. If the particles were tiny pellets, you would get 2 stripes on the screen, one behind each slit. That is not what you get. You get a pattern of many bright and dark bands, the signature of waves interfering. The same pattern you would see if you drop 2 stones into a still pond and watch the ripples cross. And you get it even when you send the particles through one at a time, with long gaps between them, so that no particle could possibly be interfering with any other. Each particle apparently goes through both slits, interferes with itself and lands. Now put a detector at one of the slits so you can tell which one each particle went through. The bands vanish. You get the 2 stripes. The particle stops behaving like a wave the moment you can tell which route it took. That is already the whole problem in miniature, and people have been staring at it since 1909. But there is a version of it that is stranger, and it is the one I want to spend time on tonight, because it is where the popular story about quantum physics and time comes from. It is called the Delayed Choice Quantum Eraser. The design was proposed by Marlon Scully and Kai Druhl in 1982. It was actually built and run by Yoon-Ho Kim, Rong Yu, Sergei Kulik, Yanhua Shi and Scully himself, and published in Physical Review Letters in the year 2000, volume 84, starting on page 1. It is a real apparatus that sat on a real optical bench and its results have been reproduced many times since. Here is what it does. A photon goes through a double slit as before, but immediately behind the slit sits a special crystal, a beta-barium borat crystal in the original, which does something remarkable. When a photon passes through it, roughly 1 time in 10 billion, that photon is converted into 2 photons of lower energy, and the 2 are entangled. Their properties are linked. The process is called spontaneous parametric down conversion, and the 1 in 10 billion conversion rate is the reason these experiments take a long time to run. One member of the pair is called the signal photon. It travels a short distance to a movable detector, which the paper calls D0, and it lands. The experiment records where. The other member is called the idler, and the idler takes the long way round. It travels through an arrangement of prisms, mirrors, and beam splitters, and eventually arrives at one of 4 detectors, and this is the clever part. 2 of those 4 detectors can only be reached by a photon whose path is unambiguous. A photon that arrived at that detector came from one specific slit, and the experiment knows which. The other 2 detectors sit behind an arrangement where the 2 possible routes have been recombined at a beam splitter, so that a photon arriving there could have come from either slit, and there is no longer any physical record anywhere in the universe of which one it was. That information has not been hidden. It has been destroyed. So each idler photon, entirely on its own, ends up either preserving which path information about the pair or erasing it. And nothing decides which of those happens except the photon itself, arriving at a beam splitter that sends it one way or the other with 50-50 odds. There is no human choosing. Wheeler's original version of this thought experiment imagined an experimenter flipping a switch. Kim and his colleagues improved on it by taking the experimenter out entirely and letting the photon flip its own switch. And the timing is the point. The idler travels further. In the original apparatus, it travels about 2.5 meters further, which at the speed of light works out to a delay of roughly 8 nanoseconds, 8 billionths of a second, which means the signal photon has already hit D0 and its position has already been recorded before its twin has reached the fork where the which path information will be either kept or destroyed. The record exists first, the choice happens after. Now sort the data, take every signal photon that landed at D0 and group them according to which of the 4 detectors its idler eventually hit. And what comes out of that sorting is the result that has launched 1,000 articles. The signal photons whose idlers ended up at the 2 erasing detectors show interference fringes, bands, the wave pattern. The signal photons whose idlers ended up at the 2 preserving detectors show no fringes at all, just a smooth hump, the particle pattern, same photons, same screen, same detector, recorded before the sorting information existed, and the pattern they form depends on what happened to their partners 8 nanoseconds later. Stand at the bench for a second and look at what this actually is. It is not much. A darkened room kept at a steady temperature, because a change of 0.5 degree will expand the aluminium of the optical table, enough to ruin the alignment. A pump laser throwing an invisible ultraviolet beam across the surface. The crystal, a few millimeters of transparent material sitting in a mount, doing its 1 in 10 billion conversion. 2 faint cones of light spreading out from it that you could not see if the lights were on and can barely see when they are off. On one side, a detector on a translation stage, stepping sideways in increments of a fraction of a millimeter, pausing at each position for a few minutes to collect enough counts to mean anything. On the other side, a run of mirrors carrying the idler photons on their extra 2.5 meters, a distance you could cross in 2 steps, and which for a photon is 8 nanoseconds and which is the entire drama. There is no bang, there is no flash, there is a computer accumulating coincidence counts, tick by tick, hour after hour, and somewhere in the early morning the numbers become a pattern, and the pattern is not the one that should be there. It is worth saying how far this idea can be pushed, because John Wheeler, who invented the delayed choice framing in 1978, pushed it about as far as it goes. His version was not a table in a laboratory, it was the sky. Light from a quasar billions of light-years away passes on either side of an intervening galaxy, whose gravity bends both paths back toward Earth. Wheeler pointed out that an astronomer today, choosing which kind of instrument to point at that light, is doing exactly what the experimenter at the bench does, deciding whether or not which path information will be available, except that the photon made its journey around that galaxy before the solar system existed. On the naive reading, a decision made in an observatory on a Tuesday determines what a particle did before the Earth had cooled. Wheeler's version was eventually run in miniature. In 2007, a French team led by Vincent Jacques published a version in Nature using single photons and a quantum random number generator that switched the output beam splitter in and out of the apparatus after the photon had already entered it. Same result. The photon behaved as a wave or as a particle according to a configuration that did not exist when it went in. You can see immediately why this experiment became famous outside physics. If the pattern the signal photon makes depends on a decision that happens after the signal photon has already landed, then the obvious reading is that the later event has reached back and changed the earlier one. The future is editing the past. Your choice now determines what a particle did a moment ago. And once you have that reading in your head, everything else follows. If particles do not have a definite history until something later asks about it, then the past is not a fixed thing but a kind of provisional record, still open, still being written. Time stops being a road and starts being a negotiation. I want to give that reading its full weight, because it is genuinely what the experiment looks like, and because millions of people have encountered quantum physics through exactly this framing, and it is the reason they find it disturbing. If your present choices can reach backwards, even a little, even statistically, then the ground under every ordinary assumption you have about cause and effect is softer than it looks. You did not do that thing because of what came before. You did it because of what came after. That is not a small adjustment. It is also not what the experiment shows, and the way it fails to show it is more interesting than the claim itself, because the correction does not make the strangeness go away. It moves it somewhere much harder to escape from. Part 4. What the eraser actually did. Here is the number the articles leave out. Take every single signal photon that hit D0 in the Kim experiment. Every one. Do not sort them by anything. Just plot where they all landed, the way you would plot the results of any ordinary double-slit run. There is no interference. There never was. The raw pattern at that detector is a smooth, featureless hump, and it is a smooth, featureless hump before the idler photons arrive at their detectors, and it is exactly the same smooth, featureless hump afterwards. Nothing on that screen ever changes. If you had walked in, looked at the total count distribution, and walked out again, you would have seen a completely ordinary result and gone home. The fringes exist only inside subsets. When you sort the photons by which idler detector fired, 2 of the 4 subsets show bands, and those 2 sets of bands are shifted relative to each other by exactly half a period. Where one has a bright band, the other has a dark one, which means that when you add them back together they cancel. Perfectly. They have to, because the total was flat to begin with, and you cannot get a different total by rearranging the same numbers. That is the whole thing. 2 papers lay this out carefully, one titled, with admirable directness, The Delayed Choice Quantum Eraser, Neither Erases Nor Delays, and a follow-up analysis called the Quantum Eraser Paradox. The argument in both is the same. No photon changed its behavior, no past event was rewritten. What changed was which slice of a fixed dataset a human being chose to look at. And that half-period shift is not a coincidence or a quirk of the apparatus. It is load-bearing, and the universe is fanatical about it. Suppose the 2 erasing subsets produced fringes that lined up in phase instead of cancelling. Then the total pattern at D0 would show interference whenever the erasing configuration was in place, and no interference when it was not. Which means the person standing at D0 could look at their own screen and tell, immediately, what was happening to the idler photons 2.5 meters away. And if you separate the 2 arms far enough faster than light could carry the news, you would have a superluminal telegraph. Quantum mechanics forbids that with a mathematical result called the no-signalling theorem, and the half-period shift is precisely the mechanism by which it is enforced. The interference is there, it is simply arranged so that nobody can use it. It is worth knowing that Scully did not build this thing to make a point about time. His original interest was thermodynamic. There is an old argument, going back to Leo Szilard and to Rolf Landauer, that information and entropy are the same currency, that erasing a bit of information costs you a minimum quantity of heat, and that this is why you cannot build a perpetual motion machine out of a clever demon who sorts fast molecules from slow ones. Scully wanted to know whether which path information could be erased in a quantum system and what that erasure would cost. The metaphysics was a side effect. The physicists who ran the experiment were asking a bookkeeping question, and the answer they got was a bookkeeping answer. And somewhere between the journal and the internet it became a story about the future editing the past. So, mystery solved. The future does not change the past. You can go to sleep, except that I do not think you should, and here is why. The naive reading of the eraser was, the photon did not have a definite history until something later asked about it. We have just replaced that with something that sounds tamer and is not. The correct reading is, the pattern is a property of a subset, and a subset is not a physical thing. It is a decision about how to group numbers, and that distinction is not a piece of wordplay. It is the difference between a claim about the world and a claim about a spreadsheet. Sit with that for a moment. The interference bands in the erasing subsets are absolutely real. You can photograph them. You can publish them. They are as real as anything in the paper, but they are not a property of any photon, and they are not a property of the screen, and they are not a property of the apparatus. They are a property of a partition, of the fact that somebody took a list of positions and a list of detector labels and matched them up. Which means the question the experiment actually poses is not about time at all. It is, what determines which grouping is the real one? The apparatus does not answer that. The mathematics does not answer that. Both of them will happily hand you the flat total, or the two shifted fringe patterns, or 100 other partitions if you invent 100 other ways to sort. Every one of those is a correct description of the same run. The theory does not contain a rule saying which partition corresponds to what happened, and that is the first appearance tonight of the thing this whole video is walking toward. Not time, not the past, the boundary. Remember what I told you in the first part. Quantum mechanics has a rule for how systems evolve when nothing is looking, and a rule for what you get when something looks, and it has no rule at all for which is which. In the eraser, that gap shows up in a very concrete way. The signal photon and the idler photon are one entangled system. If you treat the whole thing as unmeasured, the mathematics gives you correlations, the linked behavior of pairs, and no definite outcomes at all. If you treat the idler detection as a measurement, you get definite outcomes, and the correlations become a way of sorting them. Both descriptions are correct. Both are used routinely by working physicists, sometimes within the same paragraph, and the choice between them is not fixed by anything in the theory. You might object that this is a false symmetry, that of course a detector firing is a measurement, that of course something physical happens when a photon is absorbed by a photomultiplier tube, and a cascade of electrons runs down a chain of diodes and a voltage appears on a wire, and that objection feels right. But try to say where in that chain the measurement occurred and the ground disappears under you. The photon hits the first surface, an electron is knocked loose. That electron hits the next plate and knocks loose 4 more. Those 4 become 16, and 16 becomes 64, and by the end of the tube there are 1,000,000 electrons where there was 1, and a current flows, and a number increments in a computer's memory, and a file is written to a disk, and a graph is plotted, and a person looks at the graph. Every single one of those steps is, individually, a perfectly ordinary quantum interaction that the Schrödinger equation handles without complaint. None of them is marked. There is no point along that chain where the mathematics changes gear. What actually happens along that chain is decoherence, and decoherence is genuinely the best answer physics has. As the system couples to more and more of its surroundings, the interference between the possible outcomes gets spread out into the environment so thoroughly that it becomes, for any practical purpose, unrecoverable. The numbers are severe. A dust grain 1/100th of a millimetre across, floating in the emptiest part of intergalactic space with nothing touching it but the faint microwave glow left over from the Big Bang, loses its coherence in about 1/1,000,000th of a second. Put the same dust grain in ordinary air and the figure is around 10 to the minus 31 seconds. That is why you never see a chair in 2 places. It also explains exactly nothing about why you see one outcome rather than the other, and every physicist who works on this knows it. Decoherence tells you why the alternatives stop interfering. It does not tell you why one of them is the one that happened. This is the shifty split again, wearing a lab coat. Draw the line before the idler detectors and the fringes are a sorting artifact. Draw it after, and something happened out there that the sorting is reporting. The experiment cannot distinguish between those 2 readings, because as we established, no experiment can. There is one more thing worth noticing here, because it will come back later in a much larger form. Everything in the eraser depends on coincidence counting. You cannot see any of this from one side. The person standing at D0 has nothing but a featureless hump. The person standing at the idler detectors has nothing but a stream of clicks. Neither of them, alone, has seen anything unusual in their entire career. The strangeness lives exclusively in the comparison, in the moment the 2 records are physically brought into the same room and matched line by line. That is going to turn out to matter enormously. because in the last few paradoxes tonight, we're going to look at situations in which the two records cannot be brought into the same room. Not because it is difficult, because the structure of the universe prevents it. Hold that thought. We have 6 flashes to go, and the next one takes the observer out of the corridor and puts him inside the box. Part 5. 2 people, 1 event, 2 answers. In 1961, Eugene Wigner wrote an essay called Remarks on the Mind-Body Question, and buried in it was a scenario so simple that it takes about 90 seconds to describe, and so difficult that 65 years later, there are still papers being published about it every month. Wigner was not a marginal figure. He was one of the architects of the mathematical structure of quantum mechanics. He had won the Nobel Prize, and the theorem that carries his name is a load-bearing part of how physicists think about symmetry. When a man like that writes down a scenario his own theory cannot handle, it is worth paying attention. Here it is. There is a laboratory. It is sealed. Properly sealed, in the idealized sense. Nothing gets in, nothing gets out. No light, no air, no vibration, no information of any kind. Inside the laboratory is a person. Wigner called them his friend, and the name stuck. The whole scenario is now known as Wigner's friend. The friend has a quantum system in front of them. Let us say it is a single atom whose spin can be measured as either up or down, and it has been prepared in a superposition of both. The friend measures it. The friend gets a result. Let us say up. The friend writes it in a notebook. From the friend's point of view, something has happened. There was a question, and now there is an answer, and the answer is up, and the notebook says so. Wigner is standing outside the sealed lab. He has not opened it. He has not received any signal from inside it. Now here is the question. What does quantum mechanics say the state of that laboratory is? And the answer, if you apply the theory the way it is written, is unambiguous and uncomfortable. Nothing inside that laboratory has interacted with anything outside it. So from Wigner's position, the entire lab, the atom, the apparatus, the notebook, the ink, the friend's eyes, the friend's memory of what they saw, is an isolated quantum system, evolving under the Schrödinger equation, and it is in a superposition. Not the atom, the whole lab. A superposition of a branch in which the friend saw up and wrote it down, and a branch in which the friend saw down and wrote that down instead. To the friend, the measurement happened. To Wigner, it has not happened yet. Both of them are applying quantum mechanics correctly. Neither of them has made an error. They simply have different views about whether an event has occurred. Now, the first instinct of every person who hears this, and it is a good instinct, is that this is a story about knowledge. Wigner does not know what the friend saw. Of course he does not. He is outside the door. That is not profound. That is just ignorance, and ignorance is not a physics problem. Except, that is not what the superposition means. There is a very specific difference between the friend saw one of 2 things and I do not know which, and the lab is in a superposition, and the difference is that the second one has consequences you can measure. A system in superposition can interfere with itself. A system that is simply in one state that you happen not to know is not able to do that. If Wigner could perform a sufficiently delicate measurement on that entire lab, a measurement in the right basis, which for a system containing a conscious person is not something anyone can actually do, but which the theory permits in principle, he would find interference between the 2 branches. He would find evidence that both of them were still live, and the friend inside would swear on everything they own that only one of them ever was. That is not a gap in knowledge. That is a disagreement about what exists. There is a piece of history here that gets flattened in almost every retelling, and it matters. Wigner did not pose this scenario neutrally. He posed it as an argument for a particular answer. He thought it showed that consciousness must be what collapses the wave function, because the friend, being conscious, obviously does have a definite experience, and therefore the friend's mind must be doing something the atom and the apparatus cannot do. That was his position in 1961, and it is why the essay is called Remarks on the Mind-Body Question, rather than something about measurement, and then he changed his mind. Over the following 2 decades, Wigner moved away from that reading, in large part because of the scenario he had constructed. If consciousness collapses the wave function, then the collapse depends on which systems are conscious, and physics now needs a theory of consciousness before it can tell you what happens when a photon hits a plate. That is not a solution. That is an enormous unpaid bill The man who is most associated with the idea that minds make reality spent the back half of his career quietly walking away from it, and the popular version of quantum physics never got the memo. Think about what the scenario is really asking, stripped of the sealed room and the notebook. It is asking whether there is such a thing as an event. Not whether we can know about an event, whether there is one. Your entire life is built on the assumption that when something occurs, it occurs, full stop for everybody, whether or not anybody is around to see it. The car either hit the wall or it did not. The message either sent or it did not. That assumption is so fundamental that it does not feel like an assumption. It feels like the flaw. Wigner found a way to write down a situation in which the most successful theory in science declines to endorse it. For 57 years, this stayed exactly where Wigner left it. A thought experiment, kept in a drawer, brought out at conferences, generally regarded as an amusing way of dramatizing the measurement problem rather than a live research program. And then in 2018, two physicists at the Swiss Federal Institute of Technology in Zurich took it out of the drawer and did something considerably nastier with it. Daniela Frautschiger and Renata Renner published a paper in Nature Communications, Volume 9, Article number 3711. The title is one of the great understatements in the physics literature. Quantum theory cannot consistently describe the use of itself. What they did was nest the scenario. Instead of one friend in one sealed lab, there are two friends in two sealed labs, and two outside observers, one for each lab. 4 agents in total. Each of them is scrupulously careful. Each of them uses standard quantum mechanics, exactly as written, with no interpretive additions. And crucially, each of them applies quantum mechanics not just to the atoms, but to the other agents, which is allowed, because if the theory is universal, then people are quantum systems too. The logical structure they used comes from a construction by Lucian Hardy, and the details involve a specific sequence of measurements in specific bases, which I am not going to walk through here because it would take 20 minutes and would not make the point any sharper. The point is what comes out. What comes out is a contradiction. In a particular run of the experiment, one of the agents, on seeing their own result, is forced by correct quantum reasoning to conclude with certainty that another agent has already concluded the opposite. Not probably, not most of the time, with certainty in the technical sense, probability 1, and the other agent has in fact correctly concluded the opposite, also with probability 1. Nobody has made a mistake. There is no arithmetic error to find. Each agent's reasoning is impeccable in isolation. The reasoning only breaks when you try to hold all 4 of their conclusions in the same head at the same time and discover that they cannot all be true. Frautschiger and Renner's conclusion is not that quantum mechanics is wrong. It predicts the outcomes of the experiment perfectly well. Their conclusion is that quantum mechanics cannot be applied consistently to agents who are themselves using quantum mechanics, that the theory, used on its own users, produces incompatible statements about what is the case. It is worth being clear about what the paper does and does not claim, because this is the point where popular accounts usually go off the rails. Frautschiger and Renner are not saying that quantum mechanics gives the wrong answer. Run the experiment they describe and the statistics will come out exactly as the theory predicts every time. They are not saying the theory is inconsistent as a piece of mathematics. It is not, and nobody thinks it is. What they are saying is narrower and stranger. If you assume 3 things, that quantum theory can be applied to any system including observers, that different agents' conclusions can be combined into a single consistent account, and that any given measurement has exactly one outcome, then you get a contradiction, and therefore at least one of those 3 has to go. The paper has been attacked from essentially every direction since. Everett supporters say the argument fails at one step. Copenhagen supporters say it fails at a different step. Bohmians locate the failure somewhere else again. Cubists say the whole framing is confused, and here is the detail I find most telling about that pile of rebuttals. They do not agree with each other. Every school has an answer, every answer is different, and every one of those answers is a statement about which piece of reality to give up. Which is exactly what you would expect if the paradox were not a mistake in the paper, but a mirror. Part 6. 6 photons and 5 sigma. The thing about thought experiments is that they are safe. Nobody has to build them. You can argue about Wigner's friend for 60 years without ever having to worry that the argument will be settled, because the scenario requires putting a conscious human being into a coherent superposition, and that is not an engineering problem, it is a fantasy. Unless you are willing to shrink the friend. In September 2019, a group led by Massimiliano Proietti at Heriot-Watt University in Edinburgh published a paper in Science Advances, Volume 5, article EAAW 9832, titled Experimental Test of Local Observer Independence. And I want to be careful here, because this paper is routinely misreported, including in the material that prompted this video, which places it in Nature Communications. It was Science Advances. The Nature Communications paper is the Frauschiger and Renner theory paper from the year before. 2 different papers, 2 different journals, 2 different things. It matters, because one of them is an argument and the other is a machine. What Proietti's group did was build an extended Wigner's friend scenario with 4 observers on an optical bench using 6 photons. The trick, and it is the trick that makes the whole thing possible, is that you do not need a person to be a friend. You need something that makes a record. In the experiment, the friend's role is played by a photon whose polarization becomes correlated with the measured system. That correlation is the record. It is a physical fact about the world that encodes the outcome exactly as a mark in a notebook does, just smaller. And because it is small, it is reversible. That is the entire point. You cannot unsee something a human being has seen. You can absolutely unwrite a correlation between 2 photons, and having the ability to unwrite it is what lets you ask Wigner's question experimentally. If I undo the friend's measurement, was there ever an outcome? They ran it, and they measured a Bell-type inequality, a specific mathematical bound that has to hold if certain intuitive assumptions about reality are true. The bound was violated by 5 standard deviations. Stand at that bench for a moment. It is not a dramatic-looking room. It is a slab of optical table, a metre or 2 across, drilled with a grid of threaded holes, floating on air legs to keep the building's vibrations out of it. Bolted to the surface are dozens of small black mounts holding lenses, wave plates, crystals and mirrors, and the whole thing is threaded together by beams you cannot see, because the light is faint and the wavelength is near the edge of what an eye can register. There is a cooling fan somewhere, and a rack of electronics, and the room is kept dark and the temperature is held steady. 6 photons at a time make it through. The rate is low enough that a full run takes many hours, and what accumulates during those hours is a column of numbers, updating slowly, ticking upward as coincidences are counted, and the number those coincidences are converging on is a number that ought to be impossible. Somewhere in the small hours, in a building in Edinburgh, on a table you could fit in a garage, the assumption that facts are the same for everybody quietly failed to survive contact with a measurement by 5 standard deviations. Nothing on the table moved, nobody shouted. The author's own conclusion stated in the paper is careful, and it is worth quoting the shape of it exactly. If one holds fast to the assumptions of locality and free choice, the result implies that quantum theory should be interpreted in an observer-dependent way. Read what that is doing. They are not saying reality is observer-dependent. They are saying, here are 3 things you would like to keep, and you cannot keep all 3. Locality. No influence travels faster than light. Free choice. The experimenters can genuinely pick what to measure. And observer independence. An event that happens for everybody. Pick 2. It helps to know where these inequalities come from, because they are the reason any of this is testable rather than merely arguable. In 1964, John Bell, the same man who wanted the word measurement banned, proved something that had been assumed impossible. He showed that the question of whether particles carry pre-existing hidden properties is not a philosophical question at all. It is an arithmetic question about correlations, and you can settle it with a machine. If particles have definite properties before you look, and no influence travels faster than light, then certain measured correlations have to stay below a specific number. Quantum mechanics predicts a bigger number. Nature, when finally asked properly, gives the bigger number. It took 50 years to ask properly. Every early experiment had loopholes. The detectors were not efficient enough, or the measurement settings were chosen too close together in time for relativity to forbid a signal passing between them. Those were finally closed in 2015 by a group at Delft led by Ronald Henson, using electron spins in diamonds separated by more than a kilometre, and independently the same year by teams at the American National Institute of Standards and Technology and in Vienna. In 2022, the Nobel Prize in Physics went to Alan Aspect, John Clauser, and Anton Zeilinger for that programme of work. There was even a version called the Big Bell test, in which the measurement settings were generated by more than 100,000 members of the public pressing buttons in an online game. on the theory that if you are worried about the universe conspiring to fix your random number generator human whim is at least a differently shaped conspiracy. Then, in 2020, a large collaboration made the logic considerably sharper. The paper is A Strong No-Go Theorem on the Wigner's Friend Paradox, published in Nature Physics, Volume 16, pages 1199 to 1205, by Kokwei Bong, Anibal Utreras Alarcon, Farzad Ghaffari, Yongcheng Liang, Nora Tischler, Eric Cavalcanti, Jeff Pride, and Howard Wiseman, working mostly in Australia and Taiwan. They gave the assumption set a name, local friendliness, and they broke it into two pieces that can be stated in plain language. The first is called the absoluteness of observed events. It says that an event observed by any observer has an absolute value rather than a relative one. If it happened for you, it happened, full stop, for everyone. The second is called local agency. It says that an intervention cannot influence events outside its future light cone. What you do here and now cannot affect what is happening somewhere else right now, or what already happened. This is not a philosophical preference. It is the structure of relativity. Those two assumptions, taken together, generate mathematical constraints on what correlations are possible. Quantum mechanics violates them, and here is the part that makes this a genuinely new result, rather than a restatement of Bell's theorem from 1964. The local friendliness constraints are strictly stronger than Bell's. There is a region of possible correlations that Bell's inequalities permit, and local friendliness forbids. Which means this is not the old non-locality argument with a fresh coat of paint. It is a separate, tighter box, and quantum mechanics is outside it. There is a standard objection to all of this, and it is a good one, and everybody in the field knows it. The objection is, a photon is not an observer. A polarization correlation is not an experience. Calling that thing a friend is a marketing decision. Nothing in the Edinburgh experiment saw anything. That objection is correct, and it is also a trap, and watching it close is one of the more elegant things in this whole area. Because if you insist that a real observer is required, that the argument only bites when the friend is genuinely conscious, or genuinely macroscopic, or genuinely irreversible, then you owe the field a specification. How many particles does the friend need? Does it need to be alive? Does it need to be awake? Does the record need to be permanent? And if so, permanent for how long? At what point in the chain, from photon to polarization to detector to neuron to memory, does the thing stop being unwritable and start being a fact? You have just been handed the measurement problem back, gift-wrapped. The objection to the experiment is the thing the experiment is about, and people are closing that gap. In 2023, Howard Wiseman, Eric Cavalcanti, and Eleanor Riefel published a design in the journal Quantum for what they called a thoughtful local friendliness test, an experiment in which the friend would be an artificial intelligence running on a quantum computer, sophisticated enough that its status as an observer becomes genuinely arguable, and still reversible, because it is a computation. And in January 2026, a group implemented Wigner's friend circuits on IBM's superconducting quantum hardware, and benchmarked what they called an interbranch communication witness across 5 qubits. What that means practically is that the question is no longer waiting on philosophy. It is waiting on hardware. Every year, the systems that can be held in coherent superposition get bigger, from single atoms to molecules of thousands of atoms, to mechanical oscillators you could in principle see with a good microscope, and every year the space in which you can claim that a friend is too big to be reversed gets a little smaller. The scenario Wigner sketched in an essay about the mind-body problem is now something you can queue up on a cloud service. Part 7. The direction that is not in the equations. Let me tell you about a direction that is not in the equations. Everything you have ever experienced has had a direction. You woke up, then you got out of bed, then you brushed your teeth. Not the other way round. You dropped the glass, then it broke. The pieces have never once gathered themselves off the floor and reassembled into a glass in your hand. Time goes one way, obviously and constantly and without exception, and it is possibly the single most reliable fact of your existence. It is not in the physics. The Schrödinger equation, the one at the center of quantum mechanics, is time-symmetric. Run it forwards, and it is valid. Run it backwards, and it is equally valid. There is no term in it that distinguishes one direction from the other. The same is true of Maxwell's equations for electricity and magnetism. The same is true of Newton's laws. The same is true of Einstein's field equations for gravity. Every fundamental law we have found, with one small and technical exception involving certain rare particle decays, works identically in both directions. So where does the arrow come from? The current answer is that it does not come from the laws at all. It comes from statistics and from an initial condition. The universe began in an extraordinarily ordered, extraordinarily low entropy state, and since then it has been spreading out, and there are overwhelmingly more disordered arrangements than ordered ones. So the overwhelmingly likely direction of change is toward disorder. The glass breaks rather than unbreaking because there are astronomically more ways for it to be in pieces than for it to be a glass. That is not a law forbidding the reverse. It is a probability so lopsided that in the age of the universe it has never once been beaten, which means the direction of time as you experience it is a bulk effect. Zoom in far enough, down to individual particles, which is where quantum mechanics lives, and it stops being there. Some physicists have taken that seriously enough to build it into the formalism. In 1964, Yakira Haranov, Peter Bergman and Joel Lebowitz proposed what is now called the two-state vector formalism. The standard way of describing a quantum system uses one state, evolving forward in time from the moment you prepared it. Their proposal uses two, one evolving forward from the preparation and a second one evolving backward from the final measurement. The system between those two moments is described by both. That sounds like a mathematical convenience. It is more than that, because it changes what a complete description is. In the ordinary picture, you explain what happened by what came before. Why did the apple fall? Gravity, and the tree, and Newton. You do not say the apple fell because somebody was going to want to eat it later. In the two-state picture, the account of what happened in the interval is not finished until both ends are nailed down. It is like reading a novel where the meaning of chapter 1 is genuinely not determined until you have read chapter 10. Not because you have misunderstood chapter 1, but because chapter 1 is not complete on its own. This is where the word retrocausality comes from, and it is worth being extremely clear about what it does and does not permit. It does not permit sending a message backwards. There is a theorem forbidding that, and the mechanism is the one we saw in the eraser. Any backwards influence is only visible after post-selection, and post-selection requires you to already have the later record. By the time you could use the information, the future has already happened. You cannot warn yourself. You cannot change anything. What retrocausality buys you is not power over the past. It is a different accounting of what a physical event is. The two-state formalism also gave us a tool that is going to matter in about 10 minutes, so I want to plant it here. If a quantum system is described by a state coming forward and a state coming backward, you can ask what value an observable takes in between, and the answer you get is called a weak value. It is computed from both boundary conditions, and weak values behave strangely. They are not restricted to the range of results the observable can actually give. Measure the spin of a particle in the ordinary way, and you get one of two answers. Compute a weak value for the same quantity, between the right preparation and the right post-selection, and you can get 100. Whether that is a profound clue about what is really there between measurements, or a warning sign that the quantity has been overinterpreted, is a live argument that has been running since 1988, and we are going to walk straight into the middle of it shortly. There is also a philosopher's version of the argument, made most forcefully by Hugh Price in a book called Time's Arrow and Archimedes' Point in 1996. Price's claim is that physicists reject backward influence, not because the equations forbid it, they do not, but because we are creatures who remember one direction and anticipate the other, and we have quietly built that asymmetry into what we consider an acceptable explanation. His argument is that if you were a genuinely time-neutral being looking at the equations from outside, retrocausality would not strike you as exotic at all. It would just be a boundary condition. And there is a cousin of retrocausality that almost nobody wants, called superdeterminism. It says the correlations are explained by a common cause far back in the past that fixed both the particle's properties and the settings the experimenters would later choose. It saves locality and realism together elegantly, and its price is the assumption that experimenters can freely decide what to measure, which is the assumption every experiment in this video rests on, including the one that would be used to test superdeterminism. And there is a picture of time that follows naturally from all of this, which physicists call the block universe. On this view, past, present, and future are all equally real. The whole of space-time exists as a single, fixed, four-dimensional structure, and what you call the flow of time is not the universe changing, but you moving your attention along a dimension that is already there. Nothing is being created. You are visiting. The moment you had breakfast in is exactly as real, right now, as the moment you are in. That picture does not require any quantum input at all. It falls out of special relativity, from the relativity of simultaneity. If two events are far enough apart in space and close enough together in time, then different observers moving at different speeds genuinely disagree about which one happened first, and none of them is mistaken. There is no universal now, and if there is no universal now, it is hard to see what would distinguish the present moment from any other than the fact that you happen to be in it. There is a version of the block picture built directly into quantum mechanics as well, called the transactional interpretation, put forward by John Cramer in 1986. It reads every quantum event as a kind of handshake, a wave going forward in time from the source, a wave going backward in time from the absorber, and the event happening where the two agree. It is built entirely out of the time symmetry of the underlying equations, and it makes exactly the same predictions as every other interpretation, which is both its strength and the reason it has never won. Some people find that comforting. Everything you have loved is still there, permanently, at its own coordinates. Some people find it unbearable for exactly the same reason. Let me stop here for a moment and stack up what we have, because we are halfway and the pile is getting tall. We started with a theory that has two rules and no instruction for switching between them. We looked at an experiment that appears to show the future rewriting the past, and found that it does not, but that the pattern it produces belongs to a way of grouping the data rather than to any physical object, and the theory does not say which grouping is the real one. We looked at a sealed laboratory containing a person, and found that quantum mechanics gives two correct and incompatible answers about whether an event occurred inside it. We watched that thought experiment get built out of 6 photons in Edinburgh and violate an inequality by 5 standard deviations, and then get sharpened into a theorem stronger than Bell's. And now we have found that the direction of time itself, the thing you would have bet your house on, is not in the fundamental equations, and that at least one serious formalism describes quantum systems using both ends of an interval rather than just the earlier one. 4 different problems. Every single one of them has bottomed out in the same place. The theory will not tell you when something becomes a fact. Keep that in your hand. We have 3 more paradoxes to go, and each one is going to look like it is about something completely different. One is about 2 people winning a game they cannot win. One is about an object separating from what it is like, and one is about you, and whether you can die. Part 8. Winning a game that cannot be won. I want to describe a game you cannot win, and then tell you about the people who win it every single time. 2 players. Call them Alice and Bob. They are put in separate rooms, and they cannot communicate, not by speaking, not by signalling, not by any means whatsoever, from the moment the game begins. Before that, they can talk as long as they like, they can plan, they can agree on any strategy they want, they can memorize an entire book of instructions if they think it will help. Here is the game. There is a 3x3 grid, 9 squares. Alice is given one of the 3 rows at random and has to fill in its 3 squares. Bob is given one of the 3 columns at random and has to fill in its 3 squares. Each square gets either a +1 or a -1. There are 2 rules. Alice's 3 entries have to multiply together to give +1. Bob's 3 entries have to multiply together to give -1. And the winning condition is simple. Where Alice's row crosses Bob's column, there is 1 square that they have both filled in. If they put the same number in that square, they win. If they disagree, they lose. Neither of them is told which row or column the other one got. This is called the Mermin-Perez magic square game, described independently by David Mermin and Asher Perez around 1990. Now, your instinct is that this is easy. Just agree beforehand on a filled-in grid. Memorize all 9 numbers. Whatever row Alice gets, she reads off her 3. Whatever column Bob gets, he reads off his 3. The intersection always matches because they are reading the same table. Win every time. Except no such table exists. Here is why, and it takes about 30 seconds. Suppose you have a completed grid. Take the product of all 9 entries. You can compute it 2 ways. Multiply the 3 rows together. Each row gives +1, so 3 +1s multiply to +1. Or multiply the 3 columns together. Each column gives -1, so 3 -1s multiply to -1. The same 9 numbers, multiplied in the same way, giving +1 and -1. That is not a hard problem. That is a contradiction. There is no grid. which means the players cannot share a table because the table cannot be written down. And it turns out this is not a limitation of tables. It is a limitation of every possible classical strategy, including randomized ones, including ones where they agree on 1,000 different tables and pick between them using a shared coin flipped in advance. There is a hard ceiling. The best any classical pair can do is win 8 rounds out of every 9. There will always be some combination of row and column where the pre-agreed answers collide. Now give Alice and Bob entangled particles. Specifically, give each of them 2 qubits, so 4 in total across the pair, prepared in a particular entangled state. And instead of a table of numbers, give them a table of measurements, a set of quantum observables arranged into the same 3x3 grid, chosen so that the 3 observables in any given row can all be measured together, and so can the 3 in any given column. Alice gets her row, measures her 3 observables, and reads off the 3 answers. Bob gets his column, measures his 3, and reads off his 3. Neither has any idea what the other was asked. Alice's 3 answers multiply to +1, automatically. Bob's multiply to -1, automatically. And at the intersection square they agree. Every time, not most of the time, every time. They win with probability 1, in a game where it is provable that no classical strategy can. Gilles Brassard, Richard Cleave and Alain Tapp gave this class of games a name, quantum pseudo-telepathy. And the name is doing careful work, which I will come back to. This is a different kind of quantum advantage from the one people usually talk about. In the famous Bell-type experiments, the ones that won the 2022 Nobel Prize, quantum players do better than classical players on average, about 85% against 75% on the standard version. That is a statistical edge. You need many runs to see it. Here there is no statistics at all. Classical players lose sometimes and quantum players never do, and one clean round is in principle enough to tell the difference. There is a 3-player version too, invented by Daniel Greenberger, Michael Horn, and Anton Zeilinger in the late 1980s, usually just called the GHZ game. Same structure, a set of questions, a coordination rule, no communication, and a contradiction that classical strategies cannot escape and entangled ones sail through. And this is not a chalkboard result. In 2022, a team published a faithful experimental demonstration in Physical Review Letters, Volume 129, Article 050402. The engineering is neat. Rather than trying to distribute 4 separate entangled particles, they used a technique called hyperentanglement, preparing photon pairs entangled in 2 different properties at once, both their polarization and their orbital angular momentum, the twist in the wavefront. 1 photon pair, 2 entangled degrees of freedom, 4 qubits worth of resource. Their conclusion in the paper, stated with the appropriate caveats about locality and fair sampling, is that quantum players can simultaneously win all the queries over any classical strategy. So, 2 people in separate rooms, with no way to communicate, producing perfectly coordinated answers to questions neither of them knew the other had been asked. Now let me take it away from you, carefully, because this is where the internet goes wrong. Nothing is transmitted, no message crosses the gap, nothing travels faster than light. Look at what Alice actually sees. Her 3 results taken on their own are random. Uniformly, boringly random. Same for Bob. Neither of them, examining their own data for a lifetime, would ever find anything unusual in it. There is no pattern, no signal, no hint of anything. Alice cannot use this to send Bob a single bit, and she cannot tell from her own results which column he was given. The correlation exists only in the comparison. It appears when the 2 records are physically brought together and matched line by line, which requires somebody to carry one record to the other, at ordinary speed, through ordinary space. That is why it is called pseudo-telepathy. It looks exactly like mind-reading from the outside, and it is provably not mind-reading, because mind-reading would let you send a message and this cannot. But look at what it does establish, because it is not nothing. Those particles did not carry the answers with them. There is no table, so there was nothing to carry. The result at Alice's end and the result at Bob's end were not fixed until the measurements happened, and yet they came out consistent. That is a theorem, not an interpretation. It is a compressed version of the Kochen-Specker theorem from 1967, which proves that quantum observables cannot be assigned values independently of what is measured alongside them. Which value you get depends on the company the question keeps. There is one more thing about entanglement that deserves saying here. because it is the sort of fact that makes physicists uncomfortable in a way they rarely advertise. Quantum mechanics breaks the classical limit, but it does not break it all the way. For the standard two-player bell game, the classical ceiling is a number, 2. Quantum mechanics can reach 2 times the square root of 2, which is about 2.828, and no further. That ceiling is called the Cyrilson bound, and it is a hard consequence of the mathematics. But the logical maximum, the largest value you could have without letting anybody send a signal faster than light, is 4. There are perfectly consistent hypothetical devices. Physicists call them Popescu-Rawlik boxes, after Sandu Popescu and Daniel Rawlik, that would hit 4, be entirely compatible with relativity, and permit no communication whatsoever. They do not exist. Nature stops at 2.828. Nobody knows why. There is no principle anyone has found that explains the location of that ceiling, and there is a small, persistent research program devoted to trying to derive quantum mechanics from scratch by asking what extra assumption would put the bound exactly there. It is one of the stranger unfinished pieces of business in physics. We have found the edge of what the universe permits, and we cannot account for where it decided to draw it. I should also flag the honest small print on the 2022 experiment, because it is in the paper, and it should be in this video. Detectors are not perfect. Not every photon that leaves the source is registered, and the perfect win claim holds for the subset that was detected. That is called the fair sampling assumption, and it is the same assumption that Bell tests spent 50 years learning how to remove. Nobody seriously believes the undetected photons are conspiring. It is simply worth knowing that the claim is about a subensemble, and that being precise about which photons you counted is a large part of what separates this field from the version of it you meet online. And notice, again, where the strangeness ended up sitting. Not in either room, in the comparison, in the act of bringing 2 records together and finding that they agree. Hold on to that, because in 3 parts' time we're going to arrive at the one place in the universe where 2 records can never be brought together, and the whole thing is going to come apart. Part 9. The Grin Without The Cat. There is an experiment in the literature whose official name is a joke, and whose results are not. In Lewis Carroll's book, the Cheshire Cat has the habit of disappearing gradually, starting with the tail and ending with the head, and leaving the grin behind, hanging in the air by itself after the rest of the animal is gone. Alice's reaction is the correct one. She says she has often seen a cat without a grin, but never a grin without a cat, and that it is the most curious thing she ever saw. In 2014, a group of physicists published a paper claiming to have done it with a neutron. The paper is Observation of a Quantum Cheshire Cat in a Matter Wave Interferometer Experiment, published in Nature Communications, Volume 5, Article 4492, on the 29th of July 2014, by Tobias Denkmeyer, Hermann Geppert, Stefan Sponar, Hartmut Lemmel, Alexandra Matskin, Jeff Tollickson, and Yuji Hasegawa. The work was done at the Institut Lauer-Langevin in Grenoble, which operates one of the most intense neutron sources in the world. The cat in this experiment is a neutron. The grin is its magnetic moment. A neutron, despite having no electric charge overall, behaves like a very small magnet. It has a magnetic moment, an intrinsic magnetic property tied to its spin, and the reason neutrons were chosen for this rather than photons is precisely that. A neutron is massive, electrically neutral, and magnetic. You can push it around with a magnetic field without stray electric fields interfering, which means the grin can be probed cleanly, separately from the cat. Picture the instrument, because it is one of the more extraordinary objects in experimental physics, and almost nobody outside the field has seen a photograph of one. It is a single crystal of silicon. Not a stack of components. One crystal, machined out of a single ingot, with 3 thin blades left standing up from a common base like the fins of a very precise sculpture. The crystal lattice runs unbroken from one end of the instrument to the other, atom by atom, with no dislocations anywhere along its length. That unbroken lattice is what splits the neutron beam and brings it back together. The atomic planes themselves are the mirrors. It sits on a vibration-isolated platform inside a temperature-controlled enclosure, held stable to a fraction of a degree, because thermal expansion of a few atomic spacings across the crystal would smear the interference into nothing. The whole thing has to be kept still to below the width of an atom, and through it, one at a time, come neutrons, slow ones, cooled and selected, entering the first blade and leaving as a superposition travelling down two paths separated by a few centimetres of ordinary air. A neutron in two places at once, in a room you could walk through, guided by a lattice of silicon atoms nobody has ever seen. To give you a sense of what building one of these costs, the silicon ingots used are grown by the same process that produces semiconductor wafers, then selected for the rare specimens with essentially no crystal defects, then cut on a machine that removes material slowly enough not to introduce strain, and the finished instrument is treated as effectively irreplaceable. There are only a handful of them in the world. Now the measurement. The team used weak measurements, the technique that comes out of the same two-boundary formalism I mentioned earlier, introduced by Yakira Haronoff, David Albert and Lev Vaidman in 1988. The idea is to couple your probe to the system so gently that the state is not collapsed. The price is that any individual reading is almost meaningless, buried in noise. You recover the signal only by averaging over an enormous number of runs. So they probed, weakly, along both paths, for two different things, where the neutron was and where its magnetic moment was. And the answer they got was that the neutron's presence showed up along one path and the magnetic moment showed up along the other. The cat went one way, the grin went the other. Stated carefully, the claim in the paper is that the system behaves as if the particle is travelling down one arm of the interferometer, while its magnetic property travels down the other. That word, as if, is doing a great deal of work and everyone involved knows it, because the critiques of this experiment are serious and they have not gone away, and I am going to give them to you properly, because watching a field argue with itself in public is more interesting than any single result. There are three main lines of attack. The first is measurement-induced disturbance. The weak values in these experiments are not read off directly and non-invasively. They are inferred from changes in detection rates that arise from first-order interference effects, which opens the possibility that the apparatus is producing the effect it claims to be observing, that the probe, however gentle, is part of what makes the picture come out the way it does. The second is that you can reproduce the results with an entirely classical wave model. If a classical field going through the same interferometer gives you the same numbers, then whatever is happening is not a specifically quantum separation of a thing from its properties. It is interference, which classical waves have been doing since the 18th century. The third is the most technical and the most damaging. The mathematics of weak measurement is an expansion, an approximation that is exact only in the limit of infinitely weak coupling, which no real apparatus achieves. Keep the next term in that expansion, the quadratic one, and you find unavoidable back-action on the system, which means the clean inference from a weak value to a literal statement about where a property is located does not go through. You have a number. What that number is a number of is precisely what is in dispute. And this is the point where I want to say something about weak values in general, because it applies to a whole family of results, with names like the quantum pigeonhole paradox, in which three particles are placed in two boxes with allegedly no two in the same box. Weak values are not restricted to the range of values the observable can actually take. Measure a spin properly and you get one of two answers. Compute a weak value in the right circumstances and you can get 100, or a negative number where no negative number is possible. To one group of physicists, that is the whole point. It is a sign that weak values are showing you something real about the system between the two measurements, something the ordinary formalism averages away. To another group, a quantity that returns impossible values is a quantity that has been asked a question it does not answer. It is worth saying, in fairness to the technique, that weak measurement is not some marginal curiosity kept alive by philosophers. It works, and it does useful things. In 2008, Honor Hostin and Paul Kwiat used weak value amplification to detect a deflection of a light beam of about 400 femtometers, a distance smaller than a proton. That is not a metaphysical claim. That is a measurement nobody could otherwise have made, achieved by deliberately throwing away almost all of the data and keeping only the rare post-selected events, where the effect is enormously magnified. The tool is real. The argument is about what the tool is showing you when you point it at questions about where things are. And the Grenoble result did not stand alone for long. In 2023, a follow-up appeared in Communications Physics describing a three-path version, an interferometer with three arms rather than two, in which the neutron, its magnetic moment along one axis, and its magnetic moment along a second axis, all appear to take three different routes: a cat, a grin, and a second grin in three separate places. Whether that makes the original result more convincing or simply multiplies the interpretive problem by 3 is predictably disputed. Notice what the disagreement is not about. Nobody disputes the data. Every physicist on both sides of this argument agrees about what the detectors at Grenoble read. The numbers are not in question, and have never been in question. The argument is about what a property is, whether a thing can be somewhere that what it is like is not, whether a particle is an object that carries attributes around with it, the way a suitcase carries clothes, or whether it is something else, a set of correlations that only look like an object when you interact with them in the ordinary way. And once again, I am sorry to keep doing this, but the pattern is the pattern. The disagreement is about where you draw the line between the system and the thing measuring it, every single time. Part 10. The experiment nobody will ever run. This next one is the ugliest object in quantum foundations, and I want to handle it carefully, because it is the one that gets loose on the internet and does the most damage. It begins with a young man in Princeton in 1957. Hugh Everett III was a graduate student working under John Wheeler, and he had noticed the same thing everybody notices, that quantum mechanics has 2 rules and no instruction for switching between them. His solution was as clean as it was unwelcome. Delete the second rule. That is it. That is the entire proposal. There is no collapse. The Schrödinger equation applies always, everywhere, to everything without interruption. When a measuring device interacts with a system in superposition, the device does not force a choice. It becomes entangled with the system, and now the combined thing is in a superposition of device read up and device read down. When a person looks at the device, the person joins the entanglement. Now there is a superposition of a version of you who saw up and a version who saw down. Both are there. Neither is more real. You do not experience both because each version of you is a complete person with a complete memory, and each one remembers seeing exactly one thing. Everett called it the relative state formulation. Bryce DeWitt, reviving it in the 1970s, gave it the name that stuck, the many worlds interpretation. The reception was brutal. Everett presented his ideas in Copenhagen and got nowhere. Bohr's circle was not interested. He left academic physics entirely, went into defense analysis and operations research, and never came back. He died at 51. The interpretation that 15% of physicists now endorse was written by a man who was told, in effect, to go away, and did. Now the ugly part. If every outcome happens, and you continue in each branch, then consider a device that measures a quantum system and, depending on the result, kills you instantly. 50-50 odds, you press the button. In half the branches you die. In the other half you do not. But every version of you that is still there to have an experience is by definition in a branch where you did not die. That is not a claim about probability. It is a claim about the structure of experience. There is no version of you standing in the branch where you were killed, noticing that you were killed. So from the inside, from the only place you have ever been able to look, the sequence of your experiences continues. Press it again. Same thing. Again. Same thing. 1,000 times. Every time, the branches where it fired contain no observer, and the ones where it did not contain you, mildly surprised. Your subjective experience, on this reasoning, never ends. And if it never ends for a device, it never ends for anything, because the argument does not depend on the mechanism. It depends only on the branching. This is called quantum immortality. The argument is associated principally with Max Tegmark's work in the late 1990s, with earlier versions from Ewan Squires and Hans Moravec. And now I want to give you the version of this that actually frightens people, because it is not the version you have heard. The frightening thing was never that you live forever. Forever is an abstraction, and abstractions do not keep anybody awake. The frightening thing is what the surviving branch has to look like. Because think about what the argument selects for. Your experience continues into whatever branch permits it to continue, and nothing else. It has no preference for comfort. It has no preference for the branches where things went well. It is not choosing the good outcome. It is choosing the surviving outcome, and after enough iterations, the only branches left where you're still there to have an experience are the ones that required something enormously unlikely to go your way, which means, by construction, the branch you keep waking up in is the least probable one available, and the least probable survival is not the clean one. It is the one where the thing failed to fire and then failed again, and then the wall came down but not on you, and the aircraft found the one field, and everyone else is gone. You're the last person in the room every single time, and it never stops. And the arithmetic guarantees it will get worse rather than better, because the branches where you're merely fine keep getting used up. That is what people mean when they say this idea is disturbing. Not eternal life, eternal narrowing. So let me put it down, because it does not survive contact with the physics, and the person who took it apart most effectively is Max Tegmark himself. His objection is not technical. It is factual, and it is about how people actually die. Death is not a binary event. It is not a switch that flips. It is a continuum of states of progressively decreasing self-awareness. There is no moment in any real death, including the one described in the thought experiment, at which a fully conscious observer becomes a fully absent one in a single quantum step. The argument requires that step. Nature does not supply it. Tegmark's own way of putting it is quietly devastating in its ordinariness. When he gets old, his brain cells will gradually give out, so he will keep feeling self-aware, but less and less so. His stated position now is that an experimenter in this scenario should expect a normal probability of survival, not immortality, the usual odds. The second objection is decoherence, and it is fatal on its own. The scenario needs a person and an apparatus held in coherent superposition. That cannot happen. A macroscopic object in contact with air, light, and its own thermal vibrations loses coherence in time so short that the numbers stop meaning anything, for an everyday object in a normal room, on the order of 10 to the minus 31st seconds. Tegmark himself did the calculation for neural tissue in the year 2000 and found that coherence times in the brain fall short of what any quantum theory of mind would need by roughly 10 orders of magnitude. The trigger cannot even finish moving before the superposition is gone. I find that a genuinely kind result, and I do not say that often about physics. The most disturbing idea in this entire field turns out to be built on a picture of dying that does not match how anyone has ever died. It needs a clean edge, and there isn't one. There is a formal counter-argument too, published under the title Many Worlds Interpretations Cannot Imply Quantum Immortality, which attacks the reasoning from inside Everett's own framework. Its point is that the branch-weight structure that gives you probabilities in the first place does not license conditioning on survival the way the argument requires. You do not get to ignore the weight of the branches you're not in, and then keep using the theory that assigned those weights. It is also worth noticing that this problem is not new and is not quantum. Philosophers were working on it decades before physicists borrowed it. Derek Parfit spent much of the 1970s and 80s on cases involving teletransportation, a machine that scans you, destroys the original, and builds a perfect copy on Mars. Is that travel, or is it death followed by the creation of a stranger with your memories? Parfit's answer, developed across a book called Reasons and Persons, is that the question has no determinate answer, because personal identity is not the bedrock fact we take it to be. David Lewis and Ted Sider work the same ground from different directions. Everett's branching is Parfit's duplication machine, with the philosophy replaced by physics, and every difficulty Parfit found is still sitting there waiting. And there is a cosmological version that is arguably worse, called the Boltzmann brain problem. If the universe is large enough and lasts long enough, random thermal fluctuations will occasionally assemble, out of nothing in particular, a momentary self-aware observer complete with a set of false memories. And if the universe lasts long enough, there will be enormously more of those than there are observers who got here the ordinary way, which makes it uncomfortably difficult to justify the assumption that you are one of the ordinary ones rather than a fluctuation that will dissolve in a second. Nobody takes that conclusion seriously. Everybody agrees the reasoning has to be wrong somewhere. Nobody agrees on where, and underneath all of it sits Everett's real unfinished business, which is not about death at all. It is about probability. If every outcome happens, what exactly are the probabilities of? David Deutsch and David Wallace have both attempted to derive them from decision theory, from what a rational agent facing branching ought to bet. The derivations are elegant. They are also contested, and after 25 years there is no agreement, which is by now the least surprising sentence in this video. Part 11. What falls in? We have spent this whole video inside rooms, optical benches, sealed laboratories, silicon crystals, tables you could fit in a garage. Now I want to take the same question and put it somewhere it cannot be followed. In 1974, Stephen Hawking published a result that surprised him more than it surprised anyone else. He had been trying to prove something about the stability of black holes, and what came out of the calculation instead was that black holes are not black, they radiate. The mechanism involves quantum field theory near a strongly curved horizon, and the short version is that the vacuum is not empty. It is full of fluctuating fields, and the presence of a horizon changes what counts as empty in a way that produces a steady outflow of particles. The radiation has a temperature, and that temperature goes up as the black hole gets smaller. A black hole with the mass of the Sun would radiate at about 60 billionths of a degree above absolute zero. That is colder than the microwave background left over from the Big Bang, which is why every real black hole in the universe today is absorbing more than it emits. But the microwave background is cooling, and in the very far future it will fall below even that. And then the black holes will start to shrink, slowly. A solar mass black hole would take something like 10 to the 67 years to evaporate completely. That is not a long time by human standards. It is not a long time by cosmological standards either. It is a number with no useful comparison at all. The universe is about 14 billion years old, which is roughly 10 to the 10th years, and we are talking about a figure with 57 more zeros on it. But eventually, in principle, it goes, and when it goes, we have a problem. Here is the problem, and it takes 2 sentences to state. General relativity says a black hole is completely described by 3 numbers: its mass, its electric charge, and its angular momentum. That is the no-hair theorem, and it means everything else about what fell in: the chemistry, the arrangement of atoms, the structure, the words on the pages, is not recoverable from outside. Quantum mechanics says information cannot be destroyed, ever, under any circumstances, because the evolution of a quantum system is invertible. If you knew the final state perfectly, you could run the equations backwards and recover the initial one. This is not a preference. It is required for probabilities to add up to 1. So, throw an encyclopedia into a black hole. Wait a very long time. The black hole radiates, and Hawking's calculation says the radiation is thermal, featureless, characterized only by a temperature, carrying no imprint of what went in. The black hole shrinks. Eventually it is gone, and all that is left is a bath of radiation with no structure in it. Where is the encyclopedia? Relativity says it went behind the horizon, and then the horizon ceased to exist. Quantum mechanics says it has to be in the radiation. Hawking's own calculation says it is not. Don Page turned this from an argument into a graph in 1993. His reasoning goes like this: if the evaporation is unitary, if information really does come out, then track the entanglement entropy of the radiation as it accumulates. Early on it rises because each new particle emitted is entangled with what is left behind. But it cannot rise forever, because at the end there is nothing left for the radiation to be entangled with, and the entropy has to come back down to 0. So the curve must go up, turn over at the point where roughly half the black hole's entropy has been radiated away, and come back down. That turning point is called the Page time, and the curve is called the Page curve. Hawking's calculation does not produce that curve. It produces a line that rises and keeps rising, right up until the black hole vanishes and the entropy falls off a cliff. 2 shapes, one of them is wrong. Let me put you outside one of these things at the moment it matters. You're far enough away to be safe, which for a stellar black hole means a few hundred kilometers, and you have a detector and you have time, more time than the word means. The thing in front of you is not a hole and it is not black. It is a region where the sky simply stops, a boundary with the stars visibly bent and smeared around its edge, and it is almost perfectly quiet. The radiation coming off it is so faint that in a human lifetime you would count a handful of particles. So you wait. Galaxies form and disperse around you. The last stars burn out. The background cools until the sky is colder than the hole, and the shrinking begins, and it is imperceptible, and it goes on for a length of time with 57 zeros in it. And all the while, on your instrument, a single number is climbing. The entropy of everything you have collected, up and up and up for an eternity by any standard you have ever used. And then, at the halfway mark, with no announcement and nothing visible changing, it stops climbing. It levels, and it begins to fall. Nothing about the object looks different. The sky still stops in the same place. But the number is coming down, and what that means is that the encyclopedia has started coming home. That is the picture, if the Page curve is right. In 1997, Kip Thorne and Stephen Hawking bet John Preskill that it was not. That information really is destroyed. On the 21st of July, 2004, at a general relativity conference in Dublin, in front of a room full of physicists and a considerable number of journalists, Hawking conceded. He had come to believe that horizons fluctuate and leak. He handed Preskill the agreed prize, a copy of Total Baseball, the ultimate baseball encyclopedia, chosen, deliberately, because it is an object from which arcane information can be retrieved at will. Kip Thorne did not concede. He declined to contribute to the payment. As of 2024, more than a quarter of a century after the bet was made, he still has not conceded. There was an attempted resolution in between, and it is worth knowing about because of what happens to it. In 1993, Leonard Susskind, Larus Thorlacius, and John Uglum proposed black hole complementarity. Their argument was that the outside description, information smeared across the horizon and gradually re-emitted, and the inside description, an astronaut sailing through and seeing nothing unusual, are both completely correct, and that no observer can ever check them against each other, because to compare the two accounts, you would have to be outside collecting radiation and inside falling through at the same time, and you cannot. No observer sees a contradiction, therefore there is no contradiction. Hold that sentence, because we are going to come back to it very shortly, and it is going to turn out to be the most important thing in this video. Two accounts, both correct, that can never be compared. Then, in 2012, the problem got worse. Ahmed Almeri, Donald Marolf, Joseph Polchinski, and James Sully published an argument now known by their initials, AMPS, and it runs on a property called the monogamy of entanglement. A quantum system cannot be maximally entangled with two different things at the same time. After the page time, if information is escaping, each newly emitted particle must be entangled with the radiation that came out earlier. That is what the information is in the radiation means. But the equivalence principle, the founding idea of general relativity, that free fall is indistinguishable from floating in empty space, requires the horizon to be an unremarkable place. Nothing special should happen there, and for nothing special to happen there, that same emitted particle has to be entangled with its partner just inside the horizon. It cannot be both. Monogamy forbids it. So something breaks. And the option AMPS identified is that the entanglement with the interior partner is the one that snaps, which, because breaking entanglement of that kind costs energy, means the horizon is not smooth at all. It is lined with high-energy quanta. An astronaut falling in would not drift peacefully across an invisible boundary, the way every textbook says. They would hit a wall and burn. That is the firewall. And notice what it is. A direct collision between quantum mechanics and general relativity, at a specific location, with no obvious way for both to walk away. And then something genuinely good happened, and it is the part of this story the popular version almost never gets to. Between 2019 and 2020, the page curve came out of the equations. Geoffrey Pennington's work on entanglement wedge reconstruction, Ahmed Almhiri, Netta Engelhardt, Donald Marolf and Henry Maxfield on the entanglement wedge of an evaporating black hole, Almhiri with Raghu Mahajan, Juan Maldacena and Ying Zhao, deriving the page curve from semi-classical geometry, and Almhiri, Thomas Hartmann, Maldacena, Edgar Shagulian and Amihosin Tajdini on replica wormholes and the entropy of Hawking radiation. The machinery involves two ideas with unhelpfully whimsical names. Islands are regions of the black hole interior which, after the page time, have to be counted as part of the radiation when you compute its entropy. The inside becomes, in a precise mathematical sense, part of the outside. Replica wormholes are geometries in which multiple copies of the spacetime used in a standard calculational trick turn out to be connected to each other, and those connections contribute to the answer. Include them, and the entropy curve bends over at the page time, exactly where Page said it would. That is a real result, and it should be celebrated as one. But I have to give you the small print because it is in the literature and it is honest. These derivations are performed in controlled settings, lower dimensional models, specific spacetimes, situations chosen because they can be computed. There are published concerns about the replica wormhole derivation itself, and more importantly, computing the entropy correctly is not the same as knowing the mechanism. We now have very good reason to believe the information comes out. Nobody can yet tell you how a specific bit gets from behind the horizon into a specific outgoing photon. The books are balanced. The transaction is still a mystery. Part 12. The same paradox, wearing gravity. Read the last sentence of that complementarity argument again, and then tell me where you have heard it before. 2 accounts, both correct. That can never be compared. That is Wigner's friend. That is exactly, precisely, structurally Wigner's friend. The friend inside the sealed lab has 1 account. Wigner outside has another. Both are correct applications of quantum mechanics, and they cannot be brought together, because bringing them together would require the friend's record to leave the lab, and if it leaves, the lab is not sealed, and there was never a paradox. Swap the sealed laboratory for an event horizon, and the friend for an astronaut, and you have the black hole. Swap them back and you have a room in Edinburgh with 6 photons on a table. For decades, nobody said this out loud, because the 2 problems lived in different buildings. Wigner's friend belonged to quantum foundations, a small, slightly disreputable field full of philosophers and people who worried about what things mean. The black hole information paradox belonged to high-energy theory and quantum gravity, the most prestigious address in physics, string theorists and general relativists, people who worked on the largest questions with the heaviest mathematics. The 2 communities read different journals, went to different conferences, and had no particular reason to think they were working on the same thing. In 2025, 2 physicists said it out loud. Ladina Hausmann and Renato Renner, and yes, the same Renner, the one who nested Wigner's friend inside itself in 2018, published a paper on the preprint server with a title that does not hedge. It is called "The Firewall Paradox is Wigner's Friend Paradox." Not resembles, not is analogous to, is. It is worth pausing on who is making the claim, because in a field this contested, provenance matters. Renato Renner is not a fringe figure, and he is not a philosopher wandering into physics. He runs the Quantum Information Theory Group at the Swiss Federal Institute of Technology in Zurich, and his work on the security of quantum cryptography is standard reference material. When somebody like that writes a paper arguing that the great problem of quantum gravity is a symptom of a problem in his own field, the argument gets read. Here is their argument. The firewall paradox, they point out, depends on an assumption so quiet that almost nobody had noticed it was an assumption. Somewhere in the AMPS reasoning, you have to combine the infalling observer's perspective with the outside observer's perspective. You have to hold the astronaut's account and the distant physicist's account in the same framework at the same time and ask whether they are consistent. That combining step is what generates the contradiction. Monogamy of entanglement only bites once you have insisted that both descriptions apply to a single shared situation. And what the extended Wigner's friend results show, Frauschiger and Renner, Bong and colleagues on local friendliness, the whole program we walked through earlier, is that a rule permitting you to combine the perspectives of different agents like that conflicts with quantum theory, without gravity, without a horizon, with 6 photons on a table in Edinburgh, which means the assumption that generates the firewall was already known to be broken, in a laboratory, in a setting that has nothing to do with black holes at all. The firewall paradox, on their reading, is not a special crisis at the boundary of quantum mechanics and general relativity. It is a symptom of the same fundamental issue that produces the extended Wigner's friend paradox, showing up in the one place in the universe where it is impossible to look away from, and they go further than the single case. Their claim is that black hole puzzles and Wigner's friend puzzles are related by a correspondence, a systematic mapping, where features on one side have counterparts on the other. The horizon corresponds to the sealed laboratory. The infalling observer corresponds to the friend. The distant observer corresponds to Wigner. The impossibility of comparing accounts, which in the black hole case is enforced by the causal structure of space-time itself, corresponds in the laboratory case to the isolation of the sealed lab. One of those you can build with mirrors. The other one requires a collapsed star. They are the same problem. Think about what that correspondence cost the field practically. For roughly 40 years, the black hole information paradox has been treated as the great frontier problem, the place where our 2 best theories meet and fail, and therefore the place where the next theory will be found. Enormous quantities of talent have gone into it. String theory's biggest successes are measured against it. The holographic principle, Maldaceno's correspondence between a gravitational theory in a volume and a quantum theory on its boundary, the entire industry of computing entropies in curved space-time. A large part of that program is motivated by the belief that if we can just work out where the information goes, we will learn something fundamental about quantum gravity. And what Hausmann and Renner are suggesting is that a significant part of the puzzle was never about gravity, that you could have found it with 2 photons in a sealed box, and that the reason it looks like a gravity problem is that gravity is where the isolation becomes absolute rather than merely practical. A sealed laboratory is a fiction. In the real world, information leaks, and the friend's record becomes irreversible in nanoseconds, and the paradox stays theoretical. An event horizon is not a fiction. It is the one wall in the universe that genuinely holds. I want to be careful and honest here about the status of this. It is a preprint from 2025 in an active area, and it is an argument rather than a measurement. Not everyone in quantum gravity agrees, and the paper has already generated responses running the correspondence in the opposite direction. Lawrence Valaghem, later in 2025, took a Wigner's friend scenario and dropped it into a black hole to argue about complementarity from the other end. This is a live conversation, not a settled verdict. But it is not an isolated claim either, and that is what makes it worth your evening. It is one result inside a research program that has been quietly doing the same thing to puzzle after puzzle. Hausmann and Renner followed it in 2026 with a paper called The Paradox of the Third Particle is Classical, taking another problem everyone had labelled quantum and showing the label was wrong, and Caroline Jones and Marcus Müller at the Institute for Quantum Optics and Quantum Information in Vienna and the Perimeter Institute in Canada published a paper in the journal Quantum in June 2026 with the most sweeping version of the argument yet. Their claim is that the entire structure of the Wigner's friend paradox can be reproduced without quantum physics at all. They construct classical thought experiments involving the duplication of agents, no superposition, no entanglement, no interference, just copies of a person, and show that several of the conclusions the extended Wigner's friend theorems draw about the absoluteness of observed events come straight back out. And they note dryly that some of those classical scenarios would be considerably easier to build than the quantum ones. What they identify as the load-bearing element, they call restriction A. It says, a physical theory cannot give us a probabilistic description of the observations of all agents. Not quantum theory cannot. A physical theory. Any of them. And then they show it turning up everywhere. In epistemology, as the Sleeping Beauty problem, a puzzle about what a person should believe on waking when they know they may have been woken more than once. In cosmology, as the Boltzmann brain problem. In philosophy of personal identity, as Derek Parfit's teleportation cases. All of them, they argue, instances of one restriction. You cannot get reliable predictions for experiments whose results can be privately verified but not verified between people. And that connection to older philosophy is not decoration. It changes what kind of thing we are dealing with. If Jones and Muller are right, then quantum mechanics did not create this problem, and no future theory of quantum gravity is going to remove it. Quantum mechanics is simply the first physical theory precise enough that you cannot look away from it, the first one that forces the question into the laboratory instead of leaving it in the seminar room. The problem is what happens when a theory has to describe agents who are inside the world it describes, and who cannot all be put in the same room afterwards to compare notes. Remember the crack I mentioned in the second part of this video, the one the field learned to paint over and keep working. Here is what 100 years of painting has hidden. It is not a crack in quantum mechanics. It runs underneath quantum mechanics. It goes through cosmology and epistemology and the philosophy of what a person is. And at a black hole horizon, where the geometry of space-time physically prevents two observers from ever comparing their notes, it goes all the way through the wall, and there is nothing left to paint. Which brings us finally back to the question I asked you at the start. 7 paradoxes. One about time, one about observers, one about the direction of causation, one about coordination without contact, one about objects and their properties, one about death, one about the most extreme object in the universe. Which one is it? Which one is the one that actually frightens the people who work on this? The answer is that it was never 7. Part 13. The one that terrifies them. It was never 7. It was 1, 7 times. Here is the paradox that terrifies scientists, and I want to say it as plainly as it can be said, because the plainness is the whole point. Quantum mechanics does not tell you when a measurement happens, and it does not tell you whose outcome counts as real. That is it. That is the thing. It is called the measurement problem, and it has been sitting in the foundations of the theory since the 1920s, and every single paradox we have looked at tonight is that one gap seen from a different angle. Watch it. Change shape. Put the gap in an interferometer with a delayed idler, and it looks like the future reaching back to edit the past, because the pattern belongs to a partition of the data, and nothing in the theory says which partition is the one that happened. Put a person in a sealed laboratory, and it looks like two realities, because the boundary can be drawn inside the lab or outside it, and the theory permits both. Take the direction out of time and it looks like causation running backwards, because if you do not know when the outcome is fixed, you do not know which end of the interval fixes it. Put it in a game between two people in separate rooms and it looks like telepathy, because the correlation is only real in the comparison, and the theory does not say when the comparison makes it a fact. Put it in a neutron interferometer, and it looks like an object separating from what it is like, because a weak value is a quantity defined between two boundaries, and where you put the boundaries is exactly the thing in dispute. Put it in a thought experiment about death and it looks like immortality, because if no outcome is ever selected, every outcome is still there, including all the ones with you in them. And put it at the edge of a black hole, where the geometry of space-time physically forbids two observers from ever comparing what they saw, and it looks like a wall of fire. 7 flashes on the screen, 1 message. And now I want to go back to the phone, because I have been carrying that image all evening and it is time to hand it back to you. The device works perfectly, it has never failed. And every so often the screen flashes with symbols nobody can read. I told you at the start that you would want to know what they said. They all say the same thing. That is the part nobody expected. 7 different flashes, in 7 different circumstances decades apart, discovered by people who had never met, working in fields that did not talk to each other, and they were not 7 glitches. They were 1 sentence, sent 7 ways. And the reason nobody could read it is that the sentence is written in a word the theory does not contain. The word is happened. And that is why it frightens them, which is the part I promised you at the beginning, and which is not what most people guess. It is not exotic. That is precisely the problem. If the thing keeping physicists awake were some bizarre corner case at the edge of the theory, it could be quarantined, worked around, deferred, handed to the next generation with an apology. This is not at the edge. It is underneath. It is the hinge that every other question in the field turns on. It has been visible from the first year. Everyone who works with the theory knows it is there, and a century of the most capable people alive has not moved it. There is a particular kind of unease that comes from that, and it is different from the unease of not knowing. Not knowing is ordinary. Physics is mostly not knowing, and physicists are comfortable there. This is the unease of having been asked a question you cannot even establish the form of an answer to, of realizing that you have built the most reliable instrument in human history on a foundation you cannot describe, and that the instrument does not care. So what do people do about it? Here, briefly and fairly, are the answers on the table and what each one costs. You can say the quantum description simply does not apply to the apparatus, that the measuring device is classical, and that is that. This is the Copenhagen position, roughly, and 36% of physicists take it. The cost is that measurement stays undefined, and your foundational theory contains a word it cannot explain. You can say there is no collapse, and every outcome happens. That is Everett, at 15%. The cost is that you now have to explain what probability means in a world where everything occurs. You can say particles have definite positions all along, guided by the wave. That is de Broglie and Bohm, at 7%. It is deterministic and it reproduces every prediction exactly, and the cost is non-locality written into the equations in plain sight, plus a very uncomfortable relationship with relativity. You can add new physics, say that collapse is a real process that happens spontaneously, rarely for single particles and constantly for large ones. That is the objective collapse family, and unlike the others it is falsifiable, which is a genuine virtue. Experiments in a laboratory under a mountain in Italy have been steadily eliminating the parameter space for the gravity-triggered version. Nothing has been found. You can say the quantum state was never about the world at all, that it is a description of what an agent believes, and collapse is just that agent updating. That is the information base family, at 17%, the second largest block. The cost is that physics stops being about what is there. There is a further option that the popular literature overrepresents wildly, and I should name it so you know where it stands. You can say consciousness is what causes collapse, that the chain from photon to detector to eye stops being quantum at the moment a mind is involved. Von Neumann's mathematics permits placing the line there. Wigner endorsed it in 1961 in the very essay where the friend appears. And then Wigner moved away from it, largely because of his own scenario, on the reasonable grounds that a physics which needs a theory of consciousness before it can say what happens when a photon hits a plate has not solved anything. It has issued an enormous unpaid invoice. It did not appear as a leading option in the 2025 survey. It is not where the field is. It is where the internet is. Or you can say that facts are simply relative to systems, and that there is no view from nowhere. That is relational quantum mechanics, which does not solve the problem so much as accept it. Every one of those is a way of paying. None of them is free. And 100 years in, 1,101 physicists were asked, and only 24% of them believed their own answer was correct. So let me leave you with the last version of it, the smallest one, the one that's happening right now. You're lying somewhere in the dark. There is very little light in the room, but there is some. Photons are arriving at your eye at this moment, a few thousand a second maybe, scattered off the ceiling. Each one strikes a molecule of rhodopsin in a rod cell at the back of your retina. That molecule changes shape. That change opens a cascade, a protein, then 1,000 more, then an ion channel, then a voltage, and a signal moves up the optic nerve toward the back of your skull, and somewhere in there it becomes the fact that the room is dark. Somewhere along that chain, a quantum event became something that happened. There is no equation that tells you where. Not in quantum mechanics, not in chemistry, not in neuroscience. You can put the line at the rhodopsin, or the rod cell, or the nerve, or the thought, and every prediction anyone can make comes out identically. The theory that describes every atom in your body, that runs the scanner in your local hospital, and the chip in the phone beside you, and the clock in the satellite passing overhead right now. That theory cannot tell you what it means for something to have happened. Not because the mathematics is incomplete. The mathematics is complete. It simply does not contain the sentence. 60 years ago, Richard Feynman stood in a lecture hall and said that nobody understands quantum mechanics, and everybody has quoted it ever since as modesty. I think we can hear it differently now. It is not that nobody understands the theory. It is that the theory declines to say who the somebody is. That is the quantum paradox that is so disturbing it terrifies scientists. Not entanglement, not many worlds, not the eraser or the cat or the grin. It is the plainest item on the whole list, the one that sounds like a technicality until you notice that every other mystery in this field is standing on top of it. The universe is under no obligation to tell us when it has made up its mind. It has not told us yet.